like I said, cancer arrays as a consequence of extended multiple-step process, multiple mutations. Here I give an example. For example, in the colon, you have the normal epithelium, you have one mutation, and you have further proliferation. You have a lot of cells that proliferate, and that's it. This is the first stage. And then you undergo, for example, a second mutation where you form a adenoma, which is called a polyp. And they are also fine. And then there undergoes another mutation, until you form the colon carcinoma, which is the invasive one. And this actually, it's not very fast, this process, it's too long. And actually we have a lot of evidence proof that this is also the case, that to form tumor, it's a very long process. For example, here two studies involve people that already have genetic defects and they are expected to form colon cancer. So like I said, these polyps from these people have been removed and they didn't develop tumors. However, the two groups that they still have these polyps, not removed by surgery, they develop tumors. And we know that the polyp is, for example, the intermediate part of the tumor, and if we remove this, we will not get this. So you cannot get this from this. So there's normally process.
How is the polyp stage traced usually? Is it abnormality that is shown in the body, or like can you catch it at that stage?
With an otoscopy, you go inside and you see it and you remove it. Because this is inherited mutation in the study that I showed. So they have already risk of these to develop colon cancer. That's why they went to the doctor and the doctor tested them, for example.
What's the time frame between moving from like each stage to the last stage?
I'm showing now an example that is too long. This takes decades actually. Here, for example, cigarettes, we know that cigarettes are bad. They could cause cancer. And in the early 90s, people start to smoke. And here's the plot showing the cigarettes consumable increase after the in the early 90s, very dramatically. At this time, nobody heard about actually lung cancer. It was rare disease. And we know that lung cancer also can be caused by smoking. And only in the 1950s, something like this, lung cancer increased. So, and the difference between this and this is like 30, 40 years. So it takes a long time. And that's why actually cancer is a disease of all people, because we just live long to get these mutations.
But could it not also be that they just started to do more diagnosis about lung cancer at this time?
Also. So how this appears? Like I said, the tumor progression involves series of mutations, and each mutation damages something different probably. And it's kind of Darwinian also evolution. So we have, for example, a bunch of cells here at the beginning. One cell gets a mutation from a group of cells that they proliferate more than the others. And one of these group of cells that already have first mutation get a second mutation, and these cells form more aggressive cells, third mutation, until they form the aggressive tumor. So it's not only one single mutation, it's different than one. And here an example for colon cancer, for example, development. You have normal epithelium, you have hypoplastic epithelium, there is a one mutation here. You get to the second round, another second mutation, third, fourth, until you have invasive metastasis. I will go to metastasis later, and I will go to the single oncogenes and suppressor also in the next slides. So one mutation normally is not enough. You have different mutations, and this takes time in general, of course. Actually, the first experiment that has been reported that actually cancer, we can form cancer, it was in the early 90s. Peter Royce isolated virus from the chicken that developed sarcoma. It's kind of tumors in the found the tumor from the chicken, ground it in small pieces, put it through the filter, and you take the filtrate that passes through the filter, which is everything smaller than the cells, and inject it to the other chicken, and the other chicken developed tumor there. And people at that time thought that tumors actually are generated from the virus, that virus was the tumor. In this case it was, because there's also viruses that cause cancer, but not because only the virus. So people in the late 90s started again to work with this virus, and the virus actually we call it Roy sarcoma virus because he discovered it. So people took this virus and infected normal fibroblasts. They are normal cells. And normally normal cells, when they grow in the dish, when they are comfortable, they stop to grow because of contact inhibition. Because they know that, okay, there is no space, we have to stop growing. This is normal cells. However, when you infect these normal cells with this virus, which is called Roy sarcoma virus, they are transformed and they start to grow in all directions. So the people here could transform the normal fibroblast. And it was the first experiment showing transformation in vitro, actually, in situ. So these cells start to grow, and you can see here that normal cells, they start to grow here, for example, in the transformed cells, which here, in this case fibroblasts, they grow. This is the view from top, and if you see it from the side, it will be like this. So they form this tumors. So this was the first experiment to show that cells can be transformed by this virus, but we still don't know what the virus is exactly doing. So they sequenced the genome of this virus, and they found out this gene has 4 genes. This virus has 4 genes, GAT1 and M. They are genes important for the virus replication system. So they nothing to do with the transformation. Again, transformation is the changing from being normal to malignant cells or cancer cells. And they found a gene called SARC. And actually this gene was responsible for the transformation of the cells. So this gene was the bad gene. And of course they went through and they sequenced this gene, and they found that a gene was very similar to VSARC, the virus SARC was also existing in the normal chicken DNA. And this suggests, of course, that the virus SARC was gene oriented from the pre-existing normal cellular gene in the chicken. So what exactly happened? And they compare the virus, this Roy sarcoma virus, with the original virus, which is the ancestor of the Roy sarcoma virus, and they found out this is similar. And they made out this plan. So this virus went to the chicken cells and steal from the chicken cells the SARC gene and integrate it into its genome, and then infect other cells, and of course change it and make a tumor for these cells. So the virus kidnapped these genes and modified it also, make mutation on these genes, and convert this normal gene from proto-oncogene to oncogene. Is this clear? So, we know now our genome carries several such proto-oncogene, and they call it proto-oncogene. Why they call it proto-oncogene? Because it has the potential to be an oncogene. So if this gene, if the SARC gene, is manipulated or changed the formation that is more active, it will be an oncogene. In the normal condition, it's a proto-oncogene. It's very important for cell proliferation, for a lot of function in the gene, and we need it. But when it's converted to oncogene, it can also cause cancer.
Could it also start cancer in human cells then, if you inject it?
Yes.
So it's not really chicken specific or something,
No,
although it's carrying a chicken.
Of course, I mean, there's virus for chicken, there is virus for human, because they can, cell membrane